will be always some variability unexplained. And this random error is important for the model choice, and we are going to cover it in the second part of this workshop. So in very simple terms, this model, linear regression, predicts how your response variable varies when x changes, right? Those two coefficients, those two betas are so-called intercept and slope, right? And I'm going to show it in the next slide how those estimates, how those two betas are calculated. If you remember school, so probably, I don't know how's it in your country, but in Russia where I grew up, so we started like in the 6th or 7th grade, and I always ask myself, why do we need to learn all the stupid functions? Because you will never use them. Unfortunately, I was wrong, and from geometric point of view, linear regression is nothing different than just a linear function, right? So basically, you have a question. Thanks, Lydia. So basically, linear regression from geometric point of view is a linear function, a simple line, which explains the relationship between the variable x and variable y. And you have here, if you remember correctly from the school, you have here two coefficients. One is a slope and intercept. And you remember that intercept is basically the point where the regression line, the linear function, crosses the y-axis, right? And the slope is the angle showing how strong this relationship is, right? Not only strong, but also the direction of this relationship. So if it goes up, we speak of a positive relationship, right? And if it goes down, we speak of negative relationship, right? Because when x rises, y goes down. And the slope is nothing different than the steepness of this curve, right? How strong this relationship is. This is probably the most important part, to keep in mind when we'll be discussing the coding part. Right. What a computer does, so you have two variables, x and y, and you want to estimate the relationship between them. So what computer does, and of course we cannot see it, so it fits a number of regression lines. So just imagine those black dots are your data, and you expect them to be correlated in a linear manner. So basically the straight line is the best model you can select here to explain this relationship. And what computer does, it basically draws the first line and then calculates the different distances between the data points, those black dots, and the regression line, right? And basically then it sums up all the distances between the data points and the regression line, sums it up, right? Then it draws another line, which might go this way. Then it calculates the sum of squared errors, and again and again and again and again. And then you have, I don't know, thousands of regression lines. And then the computer selects only the one where the sum of those distances is the shortest. So basically the best fit. And this is when we say that actually, the output the computer gives you is the best model fit. So from this point of view, it means that this basically from geometric point of view, the best location, the best position of the regression line is related to the data. Right. A few essentials, a few terms. You can look it up afterwards. I mean, when we talk about model fit, this is probably the most important parameter here, residual sum of squares. It's nothing different than the total sum of those distances. And of course, when we're trying to fit regression line, you always want, the sum of squares to be the lowest. Right, a few things, we can skip them for now. I'm going to cover it anyway. And from this point on, I would like to switch to R. Are there any theoretical questions you feel I should answer? Nothing in the chat. All right. Then let's move to R. Right. the data we're going to work this afternoon is in the Dropbox folder. So it's a datasheet 3. So probably I need to explain a little bit what we are doing in this part. Well, this is the wonderful Australia, where the most of you are right now. So I'm based in Germany, in all called Europe, and here in the south, in the very south east of the country, there is a national park, Berchtesgaden. So here we can see, the so-called Bavarian Alps as a part of the big alpine mountain ridge. And this is where I do the most of my research. So I did my PhD on plant ecology, and I collected a lot of seeds there, germinated them under different temperatures. And then the question here was, whether seed ecology, whether seed germination patterns are somehow related to elevation species distribution patterns in this particular system. At the very beginning of my PhD, when I was collecting the data, I always wanted, well, for every collection site, I had to find out the climatic conditions. And unfortunately, because it's a kind of remote area, well, probably not as remote as some parts of Australia, I wanted to know the temperature conditions at different collection sites. And my collection sites went from 600 meters here in lowlands up to some peaks, which are to about 2,800 meters above sea level. The problem here was that I had data from a very few weather stations here, so altogether 25, located at different elevations, and some elevations of my collection sites were not present here. So I wanted basically to find out how cold, warm, the mean annual temperature of my collection sites at which I didn't have weather stations. Right. Just a short reminder how to connect your R script with the data. Right. There is, of course, you can type it in the R Studio directly, but there's a much easier option here. You go to session, set working directory. So basically one option would be to choose the directory where your files are. But in this particular case, the data in the script are located in the very same folder. So I could simply go to session, set working directory, and say to source file location. So now the software knows where the data are. We will need a few packages. I activate them, so to say. And we will be working with this datasheet, which includes data from 25 weather stations located at different elevations. And from those weather stations, I have a number of climatic parameters, something like mean annual temperature, mean temperature of January, mean temperature of February, and so on. I also calculated the grow degree days based on 5 degrees Celsius and 10 degrees Celsius. And of course, we have data for mean temperature of the vegetation period. Of course, I have some lowest temperatures from different months. I mean, you probably know it. Right. I read the data. Again, a short reminder, you can always click on this symbol here just to get an idea what you're dealing with. So you can see that everything was uploaded to software more or less fine. You can also see that we have some missing data points here, which are always noted as NA, not available. Right. Probably. And anyway, before I start any analysis, I always prefer to take a look at my data. And there is these two very basic functions, structure. So this is my data set down here. Give me a second. And here you can see how how the software imported, well, how this function imported the data into the R environment. And you can see that some variables, like the grow degree days, were recognized as characters, so basically letters. And this is what we don't want, because those are numbers, right? You can also see it here when you call summary. This is also a very handy function, providing you some descriptive statistics about your data. For example, elevation, you can see that the lowest elevation in my system is 434 meters above sea level. This is the highest point, but unfortunately some variables, which are numbers, were recognized as characters, letters. So this is a very handy function, how to transform, of course, and probably Terry showed to you, or I think many of you, if you're familiar with R, you know that there is this option. You can always change the character of your variables. So basically you're saying now to R that I want to have this variable, which is a character. I want it to be numeric. And when you run, see it's numeric, but the problem is you have quite many variables. So if you do it one by one, your code will be enormously long. And this is a very quick and handy function, how to transform all of them from characters into numbers. And of course, the names of the stations remain characters, because you cannot really transform words into letters. Right, as Terry told you this morning, so before we start playing with our data, before we run any analysis, you always visualize your data just to get an idea what is going on in there, to probably to select the proper model. And this is a ggplot command for that. Oh, my bad. So what I'm doing here, so I'm plotting mean annual temperature against elevation, right? So you remember, if you have ever been hiking in mountains, you know that the higher you go, the colder it gets. Well, very simple terms. And we know that number of climatic parameters change with elevation. So basically it's getting colder. And what we know from basically all mountains of the world, that the higher you go, the colder it gets. This lapse rate is about, well, on average 0.6 degrees per 100 meters. And what I'm doing here, so I see that there is a clear relationship between elevation and temperature conditions. Right. So it is always, of course, we could, you know it already from the literature, we would not need the second curve. But I strongly advise you to look for, so if you remember when in this short presentation, that I said that there are basically two types of relationships you might have in your data, either linear or non-linear. And of course, the type of this relationship is very essential for selecting a proper model, right? If your two variables are related to each other in a linear manner, you can apply, or you're allowed to apply linear function, linear regression here. And we know it from previous research, from the books, that this relationship is rather linear. But when you start working with your data, I strongly recommend you to look for non-linear relationships, right? And this is a very handy way to visualize it. In this particular case, we see that, well, the non-linear fit is not really that different from the linear, from the straight line, so we will stick to the blue line here. A few more handy visualization options. the all good pairs. So what you basically have here, all the variables in my data set, if you remember, I have quite many of them, are related to each other. For example, you can see that elevation is related to the growth degree days, based on 5 degrees Celsius, 10 degrees, mean temperature and vegetation period. So you can see that elevation is strongly correlated with many of those climatic parameters in my data set. There is also, so what we can do now, yes?
I guess the ones on the first column, the graphs on the first column are similar to the graphs that you, that first graph that you have, where you have
Correct.
mean temperature. So all the ones going down in that first column, they have elevation on the x-axis.
Correct. Correct.
So we can see how high elevations are associated with others. I can see the mean temperature, mean annual temperature, second to one, and minimum, the temperatures. I've seen all of those downward trends.
Correct.
Yeah.
Well, what I'm trying to say here is that there are different ways how to visualize your data, right? And this would be, a nice, simple graph. But of course, you could look for all possible relationships in your data set by using pairs. What you could also use is a old good correlation. So what I'm doing here, I'm estimating, I'm calculating the correlation coefficient after Spearman between and among all my variables. And this is basically the very same thing we saw in this graph. So you can see that elevation and mean annual temperature are related strongly in the linear matter. Here you go. And you can see it here. Well, the Spearman correlation coefficient between elevation and mean annual temperature, well, it's almost 1. It's an extremely strong negative relationship. The higher you go, the colder it gets. Well, you could also use this tool, this correlation matrix, as a standalone tool, to visualize, to report the relationship in your data. Terry, how did you do it this morning? Shall I?
Well, we used pairs. We used pairs to look at some of those germination indices.
Yes.
I think it's a nice, the nice thing about pairs, I think, is that you actually see the data.
Yeah.
Whereas here we're kind of missing that. And there is another, there is a package called gggali, which kind of does a combination of both of those things.
Right. Well, the point here is that sometimes the correlation is the only tool you can apply to your data. And in such cases, you could use this wonderful package. And here I provide a few links, just click on them. So basically hundreds of ways how you could adjust all those graphs. They might look very differently and even better than this one.
I guess the one problem with just looking at correlation or calculating correlation is that the relationship might not be linear. It might be quadratic or and if it's, for example, quadratic, there is a clear relationship, and yet the correlation could be close to 0. So the correlation number in itself can mask a very strong relationship between two variables.
Yes.
Something to keep in mind. Yeah.
And this is exactly my comment here in the line 40. So usually if you expect two variables to be correlated in a linear matter, we prefer Pearson correlation coefficient, right? But if you have no idea, and if you suspect that the relationship might be nonlinear, quadratic, whatever, so you better use a Spearman correlation coefficient because, it is calculated differently and doesn't have this assumption. Well, it could partially address this problem, but of course, as Terry said, you always need to plot your data, just to get an idea what is going on in there. Right. Shall I give you a few minutes to run the code? I mean, how did you do it this morning?
This morning I just live coded, but yeah, I'd forgotten about just running the code. But I think a lot of the commands are things that we've done in the past. So hopefully, running the code people can read the code and get a feeling for what it's going to do.
Right. Because, well, so shall I go on then, or do you need 5 minutes to reflect on the things? Because usually I teach this workshop slightly differently, in a different manner. I explain things and I let participants, to practice a little bit. Just tell me, shall I go on?
Well, I think if everybody has the part 2 code open, if they're running it at the same time as you are, Sergey, then maybe sounds like everybody's up to date and happy to move on, but it is a good chance to ask questions if you have them, but also we're very happy for things to pop up in the chat as we go. So feel free to do that too if any questions come to mind. So sorry, Sergey, no coffee for you. You have to keep going.
It's fine. It's fine. All right, then let's move on. So what we can see from the previous graphs, from this visualization exercise, that elevation and mean annual temperature are strongly negatively correlated, right? You can see that it's almost a perfect linear relationship, which is kind of rare in ecology, right? And what we want to do in the next step, we want to quantify this relationship, right? If you remember those slides, we want to find the slope and intercept of this linear function, right? Basically to explain how strong this relationship is, or how weak. Well, in R, and I guess that many of you know this function, it's very simple. You specify your model, your linear model this way. So this is a function LM. Then you open brackets. So you say that, well, I expect that mean annual temperature, and this is my response, Y, depends on elevation, my explanatory variable or predictor. Use this symbol here. And of course, you specify what kind of data the software needs to use. Right. In the next, you get the model output, a lot of numbers we are going to discuss in a moment. I need to switch back to my slides. Right. Just a few words how to interpret the summary, the linear model output. Well, always on the top, you have a line called call. This is basically a short reminder what you are fitting here. So again, the formula here, so we estimate the relationship between mean annual temperature and elevation using the ClimDat data set. Right, the next important part here are the coefficients. Well, some things in R still annoy me. And for example, this intercept. So sometimes it might be very confusing, but not here. So basically, those first two lines, estimates, intercept, and elevation, is not different from the intercept. You remember the point where the regression line crosses the epsilon y-axis. In elevation, the second number is a slope, showing how steep this relationship is and its direction. The estimates, of course, you have the estimates and also standard error. So as I said at the very beginning, the computer calculates number of estimates and then also estimates the range of errors, how precise those estimates are. Then this column here, so the software also runs a t-test. So basically it tests whether the model estimates are significantly different from 0 or not. And this way you can see the significances, the p-values in the very last column. And as a little visual help here are the asterisks showing, you know, how small or how large this p-value is. Right. If you get an estimate equal to 0, so it means that the regression line crosses the y-axis at 0 point. And if slope is 0, that means that the line, the linear function goes parallel to x-axis. What can we learn from these numbers? So if you remember this slide here, so basically slope and intercept explain, you know, this relationship between elevation and mean annual temperature here. You can translate those numbers into this simple equation. So basically, if you want to find out a mean annual temperature at a given elevation, you have to use those two numbers, slope and intercept, from the model estimate. So basically, if elevation is 0, right, the mean annual temperature at this point will be 9.96 degrees Celsius. And the slope, this number, means nothing different than that 1 meter of increasing elevation, of course it could be decreasing if you go the other way down, means that mean annual temperature will decrease by 0.0037 degrees Celsius. And this is basically those two numbers, those estimates, two beta coefficients for this relationship, right? That means that in our particular system, based on our data we have at hand, the relationship between mean annual temperature and elevation can be explained by this equation. So we know from, as I mentioned earlier, we know that the global mean annual temperature decrease along elevation gradient is around 0.6. And now our estimate, if you multiply it now by 100, it's kind of close to this number. So it seems to me that the linear model did its job very well. Right, now back to R. So once again, here it's a short reminder what we're working with. And those are coefficients the software calculated for us, and software thinks that those estimates are the best ones, you know, to explain the relationship between elevation and temperature in our data set. Right, but yeah, now just to make it clear, so here I'm using the old good basic plot function. So again, I'm plotting my raw data, elevation versus mean annual temperature. And now by using this basic function abline, I add the regression line manually. So the first parameter here, this is the intercept. If you remember, intercept is a place on the y-axis where the regression line crosses it. And the second number is the slope, showing how steep, how strong this relationship is. And I'm simply using the estimates from the model output here, intercept and slope. And this is actually the geometric representation, visual representation of the relationship between elevation and mean annual temperature in our study system. Does it make any sense? Any questions, comments on that? No? Yeah. So once again, linear regression is a very simple tool. It's like in school back then, when you draw all these lines on a paper. So basically, you know, what computer does for you, it simply estimates the nature and the power of this relationship in your data by calculating those two parameters, slope and intercept. But now I have another question for you. Do you think is our model good? Can we really trust those results? So what do you think? Can we just, go on and use those data to publish the paper saying that, well, there is a strong negative relationship between elevation and mean annual temperature in our data set? Are you happy with that? Please, thumbs up. Okay. Please be honest, and how many of you would proceed? How many of you would stop here and use this graph in the final publication? It's a very important question. Just All right.
So it looks like in the chat we've got a few comments. I don't know if you can see that, Sergey, but people suggesting some next steps that they would take.
Yeah.
So I guess they're not happy.
Okay, this is very good news for me, because many of my students would say, well, it looks perfect. It explains the things nicely. Just go ahead with it. But you're right. This is not really correct way. And give me a second. So. Right. If you remember this game, right? The main idea here, if you want to really win this game, right, you always need to feed right figures into the right holes. And the point here, and I really want, probably to print it out and hang out in your offices, that every statistical tests you apply has some assumptions. So basically every game you play has some rules you need to obey. Otherwise, of course, you could use a hammer to fit, this wooden figure in a hole, but this is not really the correct way of doing the things. And linear models, we have a number of assumptions which should be met before you can really trust your results. And there is, I have here kind of long list, well, 10 assumptions. And now we're going to discuss them a little bit and then go back to R to see how the things work in the computational software. Well, the very first assumption of linear model is that the regression model should be linear in its parameters. So basically, in layman's terms, this relationship should be linear. If you remember this slide here, right? You can only fit linear model to your data if you expect a linear relationship, but not things like that. Or of course, it could be even more complicated. It doesn't mean, however, that you could also account for quadratic or cubic relationship, well, so-called polynomial linear regressions, right? You can also account for non-linearity in your data by including quadratic or cubic terms. I'm going to show it to you in a while, how it works. But when you plot your data and see some strange curves, and you try to fit linear model, so basically a straight line, this is actually the wrong thing to do, right? You always need to get an idea what kind of relationship you're dealing with and then select the proper model. And of course, it should be linear in its parameters. Right. The mean of the second assumption here is that the mean of residuals, and residuals are basically, in very simple terms, are leftovers. That basically you fit your model to your data, and of course there will be some remaining variability, and this is what we call residuals. And the mean of those residuals should be, well, ideally it should be 0 or very close to 0. Second assumption. Well, I hate this term because it says, well, it's kind of hard to pronounce, homoscedasticity or equivariance of residuals. So basically, you can translate this assumption in very simple terms as that you model that explanatory variables you're using in your model should explain the main part of variability in your data. In even more simple terms, you should not see any patterns here in the residuals plots, right? So the variance should not increase when you move from the left to the right. Don't worry, we're going to cover all the things once again in R. Right, the fourth assumption, which is actually one of the most critical ones, that the residuals should be normally distributed. Well, there is this common misconception that the data, the predictors you use in your models, should be normally distributed, which is not true here. This is an assumption, but for ANOVA. So, right, so before you compare two groups using ANOVA, you check whether the data are normally distributed, and if yes, you go ahead, right? But here, in linear models, it's slightly different or very different. So that the error, the residual should be normally distributed. And you can see it here in this residual plot. Right. Of course, again, it's very important to think about what variables, what predictors you use to explain the variability in your data. Right. And the next important assumption here is that the explanatory variables, predictors you use, and residuals should not be correlated with each other. So there is a simple core test function here. You could do it. And if you get non-significant p-values and low correlation coefficients, means that they're not independent, that they are not dependent from each other. Well, there is 4 more assumptions which are less relevant for our case study, for our particular case where we compare elevation and mean annual temperature, but they might be important in other studies. Well, the assumption 6. So of course, when you try to fit a model, either linear, non-linear, generalized linear model, whatever, you should have some variability in explanatory variables, right? Sometimes I help my colleagues to analyze their data, and they say, well, I suspect that temperature affects my germination pattern. But in this case, we have a temperature gradient which runs from 10 to 12 degrees, right, which is comparatively short. And of course, there will be some response of seeds to this temperature gradient, but because this gradient is very short, because there is basically no variability in explanatory variables, it will not work. Well, there is a simple function, variation, just to get an idea how large this variability is. Another important thing is that you should always have, or it is recommended to have as many data points as possible. I have another case study. I'm helping my colleagues. So we have basically 10 data points. They collected seeds different years. Now we want to find out whether climatic conditions in these different years have any effects on seed viability. And we have precipitation, we have temperature, we have ozone, we have so many parameters, but only 10 data points, right? Well, this assumption may be even self-evident and intuitive, but there are still some, and quite many studies where people have like a very low number of replicates, a very low number of data points, and we try to explain basically the whole world using only 10 data points. There is this, the rule of thumb. So if you run a multiple regression, for example, you want to understand, you want to evaluate the relationship between seed germination and climatic conditions, and you include several climatic predictors into the model. So it is recommended to have at least 10 observations, 10 data points, the explanatory variable. But of course, the more, the better. But in our case, we're kind of good because we have 25, and we have 25 weather stations, and we have only one predictor, elevation, so we are good. Right. There's also some problem when you work with time series data. So anything, any changes in time, that the residuals should not be autocorrelated. So we're going to skip it for now because it's kind of complex thing. All right, the 9 assumption multi-collinearity. So basically, the explanatory variables should not be correlated strongly with each other. So here you can simply run a correlation test, for example, this correlation matrix I just show you. And probably for those of you who are dealing with very large data sets, which includes large number of different species, you also need to consider the phylogenetic relationships of those species. So basically the basic idea here that some species which are closely related to each other because they have common evolutionary history might respond to your treatments in a similar way, right? Because they have similar genomes, they have similar adaptations to the environment. So I see a question here. So let's go back to the assumption 6. Like the answer to the question is that the variability, so I would translate it, well, this is an ideal case, right? We have variability in elevation from 400 meters to almost 2000 meters, right? So this, it spans over kind of wide range, but just imagine another situation where you had something like this. So now your elevation gradient runs from 410, 411 to 435 meters, which is basically, 20 meters of elevation. I mean, the question is, so most of you are ecologists and biologists. I mean, what kind of effect would it have on mean annual temperature? How strong these changes would be, right? Basically, 20 meters is a kind of small hill, and you won't find any big differences between, the top of this hill and.
So
does it answer your question?
Yeah, so it's more that's like proportionate to its actual, like, sorry.
Yeah.
So it's more like proportionate to what variability might look like in the real world. Is that
correct?
Yeah. Okay, cool. Sorry.
Yeah, because it happens quite often that, people have, I'm an ecologist, so I used to think in ecological gradients. So people always, try to explain complex and, let's say, big stories using like comparatively short ecological gradients, right? I don't know what you're doing, but if you test, for example, seed germination along the temperature gradient, it would make sense to use a range of temperatures running from 0 to 50 degrees, right? To make, for example, the germination curve. But some people have like very short temperature gradient running from 20 to 23 degrees, and you basically see no response because, this range is very short. Right. Well, if you want to check the assumptions, whether we met all of them, well, whether we can trust the model, whether it did its job well, there's a simple function. Well, first of all, we will need 4 panels, and you simply use this function plot. M1 in our case is the model we are working with. And of course, I listed 10 different assumptions for linear models, but usually in the real world, you just consider a few of them. But we're just going to through a few of them, which are important. Well, model linearity. So usually you should not see any patterns. Okay, sorry, I need to go back to my slides. Yeah. Well, now, before you trust your model, before you report the results, you need to check how accurate your model is and whether you met all the assumptions we were just talking about. Well, in the second line, you have some information about the residuals, right? Actually, it provides you some very basic information where the residuals are normally distributed. So the median here, the middle value here should be as close as possible to 0. And also the mean, the quartiles, you can see that it's more or less normal here, it's slightly skewed. But the point here is the median should not deviate strongly from 0. Right, down here, we get also a few important numbers. But now for the model accuracy, of course, you know that what you can also read here is the R squares. So basically, the good or fit of our model, how well it explains the variability in our data. But one important feature here is a residual standard error, right? And this number should be the lower the better. So this number itself could be used to compare two different models. Residual standard error, this number, it's quite low, so yeah, good. There are some cases when linear models fail to explain the variability in your data. And you could also do a quick check here. So you divide residual standard error by the number of degrees of freedom. So in simple terms, the number of observations, and this number should be less than 1. So you can see that in our case, well, this is the case here. So the model explains data variability quite well. Right, the second number, as I just mentioned, is the R square. So basically, R square is quite similar. It's quite close to this concept here. If R square is equal to 1, it means that your model explains the variability, basically all the variability in your data. And from geometric point of view, it would mean that all data points would lie on the line. But this is not, well, such kind of relationship are extremely rare. I haven't seen one. So the number itself, the closer it's to 1, the better model fit is. It means that in this case, the R square is 0.85. So it's basically almost a perfect fit. It means that the elevation explains the most variability in the mean annual temperature in our study system. Here you can see two different R squares, multiple and adjusted. So if you run a multiple linear regression in which you have a number of different predictors, so it is suggested to report the first number, multiple R square, because the more data, the more predictors you include into the model, of course, the better fit will be, because if you basically provide more and more information, what parameters, what predictors could explain the variability in your response variable. Therefore, once you have more than one predictor, please report this multiple R square. Right, the F statistics here, it's an essential part of this approach. So basically, it provides you the overall significance of the model. So basically, it shows you whether at least one predictor included into a model has a non-zero coefficient, well, a significant effect on the variable. Well, this part is more important for multiple linear regressions. How it looks like in R. But usually, of course, it might be a lot to take in to understand all those things, but there are basically 6 assumptions you always need to consider when running linear models. Well, the assumption 1 that model linearity is that, so basically we are checking whether we picked up right model to explain the variability in our data. And usually it's very simple. You just consider this first graph here, and you should not see any patterns here, any lines, anything. So in the literature, we describe it as a shotgun shot or star sky. So basically the residuals, the leftovers, should be distributed over this graph in a random manner, so no changes. And this is the case here, looks quite nice. We also can check the residuals. As I mentioned, this value should be, well, ideally 0, but very close to it. And you can see that this number is very small, so very good. The equal variance homoscedasticity. This is also where we can see it here in this graph. So we see no patterns here. And the difference here you have, so basically those plots are similar to each other, but in this case they are scaled, well, slightly transformed. So you should not see any patterns in those two panels here. Right. Right. The first assumption is here. The normal, it's a cuckoo plot. So actually the all residual should be aligned along this line. Of course, it's not a beauty contest. There will be always some deviations, especially at the edges. But the more you use this approach, the more you use this tool, the more experience you will gain. So it looks quite nice to me. Right. The next assumption here would be that there should not be any correlation between explanatory variables and residuals. So basically, the variables you're using in your model should explain the most of the variability in the model. And this is how we run this correlation test. Well, two important numbers here. So the p-value, it should be above the magic threshold of 0.05, right? It is not significant. And the second number is correlation coefficient itself, which basically shows you the strength of this relationship. And of course, it should be as small as possible. And you can see it's quite close to 0. So very good. And the sixth assumption, and it was the last question. So we should have some variance in our data. So it should be greater than 0. Okay, this number is normally large. So we're good. It looks quite well now. One last thing here, what you can also read from these diagnostic plots, so-called influential points. So you know that some data points, some outliers, new data sets might also affect the model fit. So again, if you think back on this picture, right? If you have an outlier, a data point which lies kind of far away from the rest, of course, it will always influence, the position of the regression line. And this last point, you can see, those influential points or data points which have the highest influence on the position of the regression line. Looks quite fine here. Well, I think I have an example later on. You will see how this might look like when you have some outliers in the data. Right. Are there any questions so far? Do we need a short break? Would like to run this chunk of the code? Yes, no, maybe.
I have a question, Sergey.
Yes, please.
Do you usually check all these assumptions? Because I usually use the plot to check the residuals. And that works for me.
It's a very good point. I mean, let's say the longer you work with linear regressions, the better your gut feeling gets, right? And usually just give me a second, I'm going to share my screen. So usually I just plot, those 4 things here, 4 panels, and usually you can see immediately, whether your model worked well or not. In some complicated cases, I check all of them, right? But let's say those 4 panels are the most essential ones. Because like I said, this is not a beauty contest, and even, there will be always some deviations from the perfect picture. Just to show you that actually, the linear models, like every other statistical test, they have very important assumptions you should meet, in many cases. But I mean, those 4, the diagnostic plots belongs to the most essential part. And if you have some problems in your residuals, you should address them by selecting, for example, another kind of model, by including other variables. Well, the list goes on and on. But my point, from my experience, I can say that, let's say 60–70% of my colleagues, they don't even check the residuals, right? They have a model, they run it, they say, oh, fine, this is exactly what I expected, but the residuals are wrong. And if you make some corrections, you know, the significances disappear. And then, you know, the story sounds not as good as they wanted to hear. And yeah. So the short take home message here is that always check the residuals in your models. Please, 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 please. You save a lot of troubles. All right. No further questions? Okay. Right. Probably one further function, kind of underused. So basically, when we talk about science, as a scientist in any field, I have basically two. Well, I'm interested in two things. The first thing is that I want to describe the relationships in my data. For example, I wanted to find out whether elevation and mean annual temperature are indeed related to each other, right? To describe this relationship, and we can see from our data that, well, they are strongly negatively correlated. The power of this relationship is kind of high. So basically, the R square here tells me that the elevation explains 85% of variability in mean annual temperature. So basically, almost all of it. But if you remember, my question here was that I have 25 stations here. And what to do if I want to find out, well, these are elevations at which the weather stations are located. But I have, for example, a collection site at 645 meters, and I have no data from this elevation. I have no climate data from this elevation. What to do? The second thing, well, what I could also use here, so we establish now a relationship, right? We have here an intercept, we have an elevation, and those two numbers show me the relationship in those two variables. And now what I can do now, I can predict mean annual temperature values for the elevations. I don't have any climate data because I know that, you know, based on those 25 observations, well, for example, for some missing elevations here, I can find out the mean annual temperature. And you can also do it in R, it's quite easy. So here I'm creating a new data frame, which consists of elevations going from 0 to 2,500 meters above sea level. And what I can do, I can calculate mean annual temperature for all of those elevations based the relationship we established with the help of the linear model, right? Because the linear model tells me this is the rule how elevation and mean annual temperature are related to each other. I'm going to use here this predict function. So basically I tell software, please use the numbers, the rule from the model, and use a new data set I have just created. Well, this is your output. You can also make it a bit handy. You can save it in a separate object. And these are mean annual temperatures for different elevations in my study system, right? Of course, I can save it now as a separate file. Here you go. So now I can use those data in my research. I can say, well, if I collect seeds, oops. let's say at 2,400 meters. I have no weather station at this elevation, but based on the model, I know that the mean annual temperature on this particular collection site is 0.9 degrees Celsius. So once again, you can use this approach not only to explain the relationships, but also predict data, to generate data for the parts of the relationship for which you have no data. So it's
your model, your data actually started around 400, but how comfortable would you feel extrapolating this model to 0?
It's a very good question, Terry. I mean, it depends, and this is probably also another thing I need to mention. Of course, we use statistical tools to explain relationships, to quantify them, but you also need to use your ecological, biological knowledge. There is this wonderful paper, which is basically in every statistical handbook. So what people did, they compared the performance of male and female athletics during the last Olympic Games. They also made some predictions. We showed that by the year 2150 or something like that, the performance of male and female athletes will be similar. But we are all biologists. We know that there are some physiological differences, right? That it's not possible. And you have to be really very careful with the ranges of your data. For example, here, we know that the relationship between elevation and mean annual temperature is kind of straightforward. Therefore, if I generate data for the missing elevations below, the threshold, I would be just okay with that. But if you know that your system behaves differently in this part of the line, I would then probably just focus only on the range for which I have some data. So what would you do, Terry?
No, that makes sense to me. I think it's the question always is, how generalizable is our model, right? I guess that's what that's the underlying question. And I agree with you that it's a biological question principally.
Yeah.
So we have to appeal to our biological minds. And I think the running example was a really good one, because clearly what must be happening is that females at the moment are improving faster than males. Yeah. And so it's then in that case, if you draw a line through it, then if females have a steeper slope, that at some point they're going to intersect.
Yeah. Yes, Ella, the answer to the question is yes. But of course, like every data analysis is data specific. So it always depends on your system, on the relationships in your system. Yeah. And once again, you always need to combine, the biological and ecological common sense with the results of your statistical output. Because sometimes you get the perfect model fit, but the results do not make any sense from the biological point of view, right? All right, so I have a few more examples how you could use this framework to address some seed ecological questions. So we will need a few of those packages you already know from earlier, tidyverse, Geminar to calculate the seed germination characteristics. And now we have another data set. So basically you have here two species.
So Sergey, there is a question from Chantal about, I've been told that, and I not really understand the question, but maybe it's worth talking about. I've been told plots should usually be presented based on modeled data as opposed to raw. I think that you're actually showing both, aren't you? You're showing the raw data and the model, which.
Yeah. So basically what ggplot does here, I mean, the black dots here are your raw data. Well, this is what you observed in the real world, right? And the blue line here is the best explanation, well, based on our calculations, based on our code. This is the best explanation for the relationship between those data. Of course, what you could do now, you could simply, generate new data. I'm going to do it this way. And, just present the predicted data. But of course, you will get a perfect straight line because you use, the linear relationship to explain the relationships in the data. So the common procedure is, the industry standard is that you plot your raw data and show the model fit. So probably one last thing here would be to add an R-square value, just to show, how well this model fits to your data. And sometimes people, they also show the expression. So basically the intercept and slopes, how those two variables are related to each other. And this is it actually. So Chantal, does it answer your question? Yeah, you could write a message to the chat. All right. All right. So the thing is, linear models are good not only for explaining relationships, but also for predicting them, for generating data, for the ranges, for the parts of this gradient, in this case, for example, to generate missing data. Of course, you have to be careful with that. Right, what we're having here now is another data set. So we have two plant species, Anthoxanthum alpinum and Anthoxanthum, sorry, it's another data set. So what I'm doing here, I have a poaceae, a grass, Anthoxanthum alpinum, growing at high elevations. I have several fluctuating temperatures, tested temperatures 10 to degrees. So I basically want to find out whether seed germination, this species, is affected by temperature. I think you did this exercise with Terry this morning, and many of you know how seed germination data usually looks like. So this number of counted seeds, of sown seeds. Then we have also different counting times, and I count number of germinated seeds. Right, it's a good idea. Just a little recommendation before you start working with a new data set. You clean up the environment. You simply delete everything what is hanging around here. You can even restart your R software if you like. Now we read data. We check its structure, so everything looks fine. I'm using here the Germinar package to calculate seed germination percentages, right? I mean, everything what you already know from earlier. So what I have here, I have 6 test temperatures, right? And yeah, the Germinar calculates a lot of seed germination parameters for me, but I'm interested in germination percentages only, right? So basically I'm subsetting now data set. I don't need all of those. So I'm cutting it down. So this is what we're dealing now. We have 6 different temperatures, 8 replicates per temperature, and we have germination percentage, which runs from 0 to 100%. If you remember, before we fit any models, we want to visualize the data, and it's like a very quick and dirty solution. So we can see that, that with increasing temperature, the germination percentage and Anthoxanthum alpinum also increases. Right? It's an atypical alpine species. We see that it doesn't really like germination at low temperatures because it's kind of risk avoidance mechanism, because after the snow, if you germinate right after the snow melt, well, meaning low temperatures, you might be killed by the very first frost event, which might occur quite early. So therefore, you wait until temperatures rise up, which indicates basically the species that, you know, the freezing period, freezing freeze is over. So, and what I would like to do here, I would like to find out whether, you know, there are some statistical differences in seed germination percentage among those 6 test temperatures. Right, a kind of trivial task. I think many of you do it like on daily basis. You have different treatments, you get your response, whatever it is, seed viability, seed germination, emergence from seed bank, and you want to find out that a certain treatment is good or bad for your study species. The good thing about the linear model framework that it could also work with factors. So you see, you have here groups of factors. You don't see it looks differently than our previous example. But the true beauty of this approach is you can also work with factors. It's groups. You can make so-called group comparison. So it's quite similar to ANOVA. So basically, you know, the calculation is identical to ANOVA. And this is how you fit the model. So you say, I want to find out whether germination percentages in those I collected from those 6 temperatures differ from each other. And I'm using this data set here. I run the model. So I get a lot of significant results, a lot of numbers. The R-square is high, so happy about it. But as it stands here in the code, and this is what the majority of my colleagues do not do, before you start thinking about the results, what they mean, you know, what is their biological, ecological importance and meaning, you have to make sure that you picked up the right model, right? Therefore, you have to take a look at the assumptions and the residuals before, not after. And this is how we do it. Simply plot it and take a look at the residuals. Once again, so later on, when you watch this recording or working with code alone, you can read the slides I prepared once again. But the residual check for very beginners is as simple as that. So you should not see any patterns here, up here and down here. And the dots should be aligned along this dotted line. So at the first sight, everything looks just fine. So it means that the model fits quite well to the data. So now let's break down this kind of complicated estimate. So intercept. So usually you can see that here we have different test temperatures, 14 degrees, 18, 22, 26, and 30, but the temperature 10, 2 is missing. It's hidden here behind this intercept. And when you compare groups using the LM framework, so basically there will be always so-called reference group. So in this case, this is the estimate germination percentage for the temperature 10, 2. So the estimate here is that on average, seeds of Anthoxanthum alpinum germinate like 17, you have 17% germination, plus minus 3.4. Of course, there is always some error in these estimates. We have a t-test and a p-value indicating that this value is significantly different from 0. Right? So basically, meaning that at this temperature, we have some germination. Now, and it's a bit confusing, or actually very confusing here. The next number, the next estimate for the temperature 14.6. Let me think about it. This actually is the difference. It's not the estimate for, it's not average germination percentage at the temperature 14.6, but the difference between germination at 14 degrees to the germination at 10 degrees. So basically you need to sum up those two numbers to get the raw number. Right, and then to basically intercept the discrimination percentage and the temperature 10.2 is a reference group, and the output simply indicates that, you know, the discrimination at 14, 18, 22, 26, and 30 degrees are statistically different from this group. However, the problem is that when you change the reference group, so I could also code it here, not going to do it. Those numbers, and most importantly, the p-values, might look like very differently. So therefore, like in ANOVA, what we need to do here is to run a post hoc test. So basically now we need to compare 10 versus 14. Well, this actually is done. So now what we're doing in the post hoc test, we're taking now another reference group, 14.6, and compare germination at 14 degrees to germination 10 degrees, to germination 18, 22, 26, and so forth. There is a wonderful package, means, and this is how you run a Turkey post hoc test. You probably know it from if you're an ANOVA user. First of all, say it again. Was it a question? All right. So once again, so here in this model output, you just get an idea whether some of your parameters are significant or not. And if you deal with groups, you always need to run a post hoc test. And this is how you do it. You get this very simple output, right? These are the estimates, recalculated estimates for your temperatures. Again, you can see that the average germination percentage at temperature 10 is 17%, 14.6, 36, and so on. You also have standard errors, and you can also use the coincidence intervals if you want to. So basically, we'll show you how precise, how good those estimates are estimated. And then here you have contrasts. For example, this function compares the germination at 10.2 and 14.6 degrees Celsius, and you can see that the p-value is lower than, you know, the magic threshold 0.05. So you can see that the seed germination percentage at temperature 14 degrees, which is 36%, is statistically different from the germination percentage at 10 degrees. Right. And then, you know, so what you could do now, you make a nicer plot. See it now. So if you want to use those data in a publication, you prepare a nice graph. You run this code. Right, you compare seed germination, and you could use, for example, different letters to indicate the statistical differences along this temperature gradient. Are there any questions on group comparison? So in such cases, I either think that either everything is too simple or it's too complicated and you got lost. So please give me any kind of feedback. No?
I see people doing thumbs up
there, Sergey.
and some nodding.
All right. Probably one more comment on this group comparison using the LM framework. So in the first example,
Sergey, there is one question.
Yes, please.
When would you use an adjusted R squared?
Like I said, an adjusted R square you use when you have well, here, for example, right? So, no, sorry, it's wrong. So as long as you have more than one predictor in your model, right? For example, I have also some other data from my germination experiment. It could be, I don't know, water level or whatever, irradiation. The more variables you include into the model, the better fit will be automatically, because basically you provide more and more information what kind of predictors could influence, in this case, germination percentage. And you need to account for it. And this is what the multiple R-square does, right? So adjusted R-square you use only when you have one predictor. If you have more than one predictor, you use this number. But usually they do not differ from each other strongly. It's like 0.1001 or so, something like that.
I reckon that answered that one. There's another question. Could you talk again about the outputs from the post hoc test?
All right. So if you're familiar with ANOVA, and I'm sure that many of you are, so basically every ANOVA test consists of 2 steps, right? Or actually 3 steps. Step 1, you check for assumptions. We know that ANOVA has a number of assumptions. The data should be normally distributed and so on and so forth. Check, it works. So the second step is you run the test, right? And ANOVA output says that, you know, there are some significant differences. Step 3 is to find out how different groups you consider differ from each other. And this is where we need a post hoc test, right? Here, it's not, well, what I'm showing here is not really different from that. So you run first this model. It basically tells you, there are some significant differences in germination percentage among the tested temperatures. And then in the post hoc test, what I'm doing here, I'm simply comparing all those groups to each other. And here you can see 2 things. This is a mean germination percentage for the temperature 10.2, 14.6, 18.10, and so on and so forth. You can see that those numbers are close to the plotted values. And then you simply, what the software does for me, it simply compares temperature 10.2 to temperature 14.6, right? I can see that this value is significant. So therefore I would use different letters, A and B, for example, to show that the germination percentage at temperature 10 and 14.6 differ from each other statistically. That germination percentage at temperature 14.6 is significantly higher than germination percentage at the temperature 10.2. Right, and then it goes, you compare 10.2 with 18.10 and so on and so forth. Does it answer your question?
Yep, thanks heaps. Yep.
Yeah. All right, Lydia, should we have a break?
Yeah, if you're happy to do that, that would be great. We did try and do a group photo this morning, but we realized you weren't here yet. So if everybody is okay with it, I'd love if we could try again. And also while no one's sharing screens, it'll make it a lot easier. And so what we have to ask to get everybody, all the pages of people, is for everyone to hold their smile for 10 seconds if you can. So I'll do a countdown again and just keep on smiling. So 3, 2, 1, smile. And
Keep
hopefully
smiling,
that's
everyone.
given. Oh, keep smiling.
Keep smiling. Sorry, there's so many people on the call. I just want to make sure I capture everyone. Thank you. You all look great. Just a few more seconds. Thanks, everyone.
Thank you, Amy. I did have one question of Rocco's from earlier, Sergey and Terry. It seems like a lot of people have had a bit of an issue where the plots are opening in a separate window rather than down in the plots window. We just wondered if you had any thoughts on why that might be. I think Rocco suggested maybe it was a version.
Well, it's not actually a problem at all. The problem is that I have very weak eyes, and well, usually I work on a very small screen. So if I plot everything in the RStudio, everything looks very small to me. And there is all good X11 function, and I think this is a question. So basically, it calls now a separate window, and I can plot, for example, this graph in a separate window, right? So I can make it bigger, for example, move it to another screen if I'm working on two. So basically, it has the very same functionality as a function in the RStudio, but I know that this function doesn't run on Mac computers, and I think this is the issue here. I mean,
Okay.
if you're happy with this window here, just stick to it. It's like for those
Okay, I think that window there in RStudio, it's not working. Like by default, they run the code for the plot and it opens it in a separate window instead in the bottom right corner of RStudio. I'm not sure why. Like I have no clue of why this is.
Are you a Mac user?
I am a Mac user, but I'm not the one having this issue. Like I'm one of the helper, and I've had a couple of people asking me this, and I don't know how to help them. So I was just wondering if you.
Well, just Google it. I mean, I had this issue last winter. There is apparently a solution for that, but I mean, just ignore it. It's not really essential here.
Yeah, I guess as long as people can find the other window and see the plot, hopefully they've got something there. Sorry, Terry.
Yeah, so I have been Googling it. And I think the issue is that, it's pretty much as Sergey said, that you can open up a device, a graphics device, and RStudio already has a default graphics device, and that's the thing that you see in the plots window. That's the graphics. So I was talking to someone in the chat, and when she writes, I think it's dev.cur and then open close brackets, so device current, she's getting her device as something called Quartz, whereas when I do that, I get something that says RStudio GD, which is RStudio graphics device. So it's really a matter of changing that default device, but the problem is that the default graphics device should be this RStudio GD, and I'm not exactly sure how to change the default.
There's the option function, options.
Yeah,
I remember I said that to someone, but I can't find.
Yeah, so there is an options function, and whether you can write device equals RStudio GD.
Yes, exactly. Options, open brackets, device equal, and in quoting marks, RStudio GD.
Maybe you could just write that in the chat.
Yeah, I'll do it.
Yeah. But it's a little bit surprising because you would think that that would be the default.
But like I said, for those who are just starting to explore the wonderful R world, you don't need to do. I think we had this short discussion before we start the main session. I always tell my students that learning R is like learning a new foreign language, right? Of course, let's imagine you have a language which has, I don't know, 100,000 words in it, and you don't use all of them, right? You have a set of words or sentences or expressions you personally prefer to use. And if you're not, well, if you draw a parallel here, some things in the code we wrote together, this is how we see the things, right? If you have another solution which does exactly what you expect your computer to do, just stick to it, right? Don't make things too complicated. If this X11 graphic design doesn't work for you, just ignore it for now. Of course, later on, when you're more familiar with software,
So I just say with Rocco, with Rocco's chat, it should be a lowercase o. It always, when I try to write commands, it always, that's the default, is to put upper case. So
Yeah,
you
sorry.
lowercase o. I know that you wrote it that way, but yeah.
Yeah, there is an autocorrection in the chat.
Yeah.
So is it okay if I leave for a few minutes?
Yeah,
I
so I
mean-
think we restarted.
Sorry, I was just talking on mute saying that I would love us to have the break. I'm sure people would like some time
Yeah.
away from their computer. There is one more question in the chat that maybe we can respond in writing in the chat, but we'll give everybody a break to sorry, what am I looking at? 3 o'clock. So, and about 20 minutes from now, if you can go on mute and cameras off for 20 minutes, and then we'll come back and get stuck into the next session. And about the recordings, so as you know, we've been recording the sessions as we go, and those will be made available. It'll just take a little bit of time to process those, and when they're ready, you'll receive an email with a link so that you can access that material. So if you just can hang on a little bit longer, they'll be with you very soon. I think that's it for updates. So I'll hand it back to you, Sergey, to take us into part 4, generalized linear models. Thank you.
Right, thank you, Lydia. So before we move on, there is one unanswered question. So I cannot really read this name properly. So he or she asks why Turkey used as a post hoc test for mean-wise comparison. What would be the rule of thumb to follow? Well, the honest answer is that I don't know. Well, Turkey post hoc test is kind of industry standard, right? If you make any group-wise comparisons, you always use this test because, as far as I know, other tests are more strict, right? And we might, destroy the significance of your results. But honestly, I don't know. So maybe Terry has her opinion on that. Terry?
My opinion on post hoc on multiple.
On Turkey, why Turkey but not other tests?
Oh, well, so the idea is that the p-values, if you don't adjust, are not really meaningful. So the idea is that we want to create sort of again measures of evidence that are honest measures of evidence. So if we ask multiple questions, then a p-value should have a meaning, something around given the complete null hypothesis, what is the probability that you got the outcome or something more extreme? Yeah. So now the complete null hypothesis is that there are no effects whatsoever. So rather than the ordinary p-value, which is a measure of evidence against a single hypothesis, this then becomes a measure against everything being nothing, all of the hypotheses being the null. So Tukey's idea was to say, well, I guess it's this sort of issue that if we have, well, no, that wouldn't be a good way to put it. So the Bonferroni adjustment is the adjustment that Sergey is talking about. It's the most conservative adjustment, saying we make absolutely no assumptions about any of these hypotheses. And so what is so this represents a measure of evidence that's where we adjust the p-values, but in a way that's the most conservative. The Tukey adjustment takes into account, it's usually in the sense of I have multiple groups, and I do expect, I have multiple groups, and I do expect there to be differences. what is the largest difference that I would expect to see in the means when there's in fact nothing going on. And that's a more specific adjustment than just saying, well, we know nothing about these hypotheses except that they're just random hypotheses. So because Tukey tries to be more specific about the family of hypotheses it's looking at, it doesn't adjust as it doesn't take as hard a hit as a Bonferroni. Really, I think that really Sergey is right in the sense that we tend to make the adjustment according to what the community is willing to accept.
Yeah. So probably one more thing to add, of course, as far as I know, there are some other post hoc tests, for example, home, which are more conservative, right? And if you want to if you want to make sure that you really do have the signal in your data, as for example, temperature A, well, germination response at temperature A is really different from temperature B, you could just take another test, because as Terry just said, the p-values have been discussed whether they're correct, the p-hacking issue and so on. And there's also some, let's say, history or field-specific attitude, to the test you apply. For example, if you're a nuclear physicist, right, you really need to make sure that the things in your system work as you expect them to do. And therefore, the p-values in the physics, for example, nuclear physics, are much lower than our matrix 005, right? Because sometimes people say that p-value actually a measure of amount of signal in the data, which is not entirely correct. Then in our field, the p-value threshold of 0.05 would be fine, would be just sufficient to say that there are some impacts of certain factor on my system, on my variables, but in some fields, the threshold might be different. And therefore in physics, they would use different post hoc comparison tests like home or other tests because they're more conservative. Right, before we move to the generalized linear models, I have a few more exercises which are relevant here. And now we're going to work with another data set, which is this data file. So you can see I have here different species collected at different elevations, right? These are my sites in the Bavarian Alps. And I tested their germination along the very same temperature gradient we just discussed. I just coded them. Well, I don't use numbers, I use letters here. A is 10.2, B is 14.6, and so on and so forth. And for every temperature, for every species, I calculated mean germination time. So basically, it's a measure of germination speed. The larger this number is, the longer seeds take to complete the germination process. I think in this mean germination time, I calculated with the help of Germinar package. Right, and in this study, I want to find out whether mean germination time is somehow related to species occurrence along this elevation gradient. And my working hypothesis here was that alpine species tend to have slow germination, in order to spread, because they germinate in a very hostile, harsh environment. So therefore, they have to spread the risks. And by germinating slowly, you always have a chance that at least a part of your seeds, even if the majority of them will be killed by frost, will be able to establish and survive. And there are actually a few ways how to test this hypothesis. I'm going to demonstrate it in a while. So before we start, in new analysis, I clean up the environment, upload the data, take a look at the data structure using the basic structure and summary functions. I can see the common problem that some variables, for example, mean germination time, were uploaded as characters, but not numbers. I need to make some adjustments here. And now it looks just fine. So I have 6 tested temperatures exactly like here, but coded as letters. I have elevation as a number, I have mean germination time as a number, and also sites. Right. Yeah, you can also see some notes in the code. So in the case you will be watching the recordings afterwards or working with the script on your own, you can also get some information here. Right, of course, before we move to the data analysis, we plot our data, and there are actually a few ways how to do it. For example, here I plot the relationship between elevation and germination speed, mean germination time, for every temperature separately. Right, I can see that, but I can learn from this graph that first of all there is apparently a linear relationship between germination speed and elevation. I can see that the data, the plot somehow confirms my hypothesis. I can see that alpine species, seeds of alpine species prefer or germinate comparatively slowly as lowland species. And I can see that there are some differences. I can see that the temperature A, which is 10.2, the lowest temperature in my experimental design, I can see that in general, plants cultivated, seeds cultivated and incubated at this temperature, will take longer, right? Because the intercept is higher. You get here a warning message, and the thing is that I have some missing values in the table. For example, here, so at this temperature, at the temperature 10.2, I had no germination in this species, therefore I could not calculate any germination speed because you need some data. And when you plot it, when you use the ggplot package to plot the data, so it automatically removes the non-available data and A's from your data set. And this is basically a simple warning that, hey, I plotted the data, but I did not consider the missing values because the software cannot really work with missing values. Just a short reminder that you could use a number of different options to visualize your data. And this is what we call faceting. So basically now I make a separate graph for every test temperature, A, B, C, D, and F. So basically it's the very same graph, but plotted in a different way. Right, and there are a few options how to specify the model, how to test my hypothesis. And by using this syntax, I basically ask the question whether the mean germination time is affected by elevation or related to elevation, right? Whether alpine species germinate with different speeds than lowland species. I run the model. I mean, the output should be familiar to you. What I can see here is that elevation does have a positive significant effect on mean germination time, meaning that alpine species do significantly germinate with a slower speed as compared to lowlands. So this is what we call a slope and intercept model. So basically the model calculates you an intercept, right? The point at which the regression line crosses the y-axis, and intercept. So basically, well, it estimates the power of the nature and power of this relationship. In this particular case, I'm not really interested in intercept, right? I don't really care at what speed seed germinates when elevation is 0. But for me, what is important here, whether this parameter has an effect on seed germination and what are the quantitative characteristics of this relationship. Right. But we could also, when we talk about the psychological gradients, the relationships might be non-linear. And there is an option to include, to account for this non-linearity using the LM framework. I might assume that, the relationship between mean germination time and elevation might be non-linear. So it doesn't really go consistently up, but there might be, a kind of fast increase starting from a certain elevation. And this is how I account for it. I include, this quadratic term into the model. And this is how the output looks like. And you can see that the quadratic term is not significant. The p-value is above the magic threshold 0.05. meaning that the MGT elevation relationship is linear. There is no linearity in it. So I can skip this part of the hypothesis, of course. Now, if you remember, we test here, we have 6 test temperatures, and I could assume that this relationship, you know, the power and nature of this relationship might be also dependent on test temperature, right? And for example, here I could include an interaction term. And by doing so, what I'm doing now, I'm fitting actually not one regression line, but a few of them. And here in the output, well, the output looks now a bit longer. And now we're going to break it down. First of all, the intercept line is you can see the temperature A is missing in the output, but it is still there, but hidden behind this intercept term. So basically, in this particular case, intercept is means an intercept for the temperature A, means that at 0 meters of elevation, the mean germination time for the seeds tested at temperature 10.2 is 1.5 or 15 days, right? The second elevation, this is a slope for the temperature A, and it's hidden here. And the rest are the differences, like in our, similar to our example when we compare different groups. This temperature B is a difference in the intercept estimate to the temperature A. So the temperature A was selected here or was set here as a reference group. Right, what we can see here, that intercepts for every test temperature A, B, C, and so on are significant. It means that the mean germination time at elevation 0 is significantly larger, is significantly different from 0, right? The second important finding here, that elevation, the slope is significant, meaning that there is a significant, statistically significant relationship between mean germination time and elevation. And you can see that the slopes for all those temperatures, their p-values, again, we compare slope for the temperature B to the slope of the temperature A. You can see that it's not significant, meaning that the relationship between elevation and mean germination time is the same at every test temperature, right? Basically, it always goes up, right? But the only difference is that this intercept. So basically, what we can see here in the graph, the lines have the same geometric parameters, right? We go up with the same slope, there's similar steep, but the intercepts here are different. Meaning that overall test temperature has an effect on seed germination speed, which is actually logic. You know, the higher temperatures, it's a basic chemistry in biology, the higher test temperature, the faster chemical and biochemical process run, and therefore fast germination is. Are there any questions so far? Is it clear enough what we're doing here by using this interaction term? Yes, no, maybe. All right. All right. Okay. Yep. Now, but what we learned earlier today, of course, these are nice results and they might make a perfect ecological sense. But before I report them, before I put them into paper, I have to check whether I made all the assumptions for the linear models. And this is the way. So we're testing now. We're working with this particular model where we have an interaction term. Basically, we fit 6 regression lines to our data, 1 line for a test temperature. And this is how our data, well, how our residuals look like. do you see any problems with the residuals based on the things we discussed earlier today?
Heavier towards the left.
Say it again, please.
It's heavier on the left.
Yeah, so you can see this V-shaped pattern. You can see when you, in this graph particularly, when you move from the left to the right, you can see that, the variability increases. Well, it might look perfectly well. It's a kind of border case, because when you take a look at the scaled residuals, this pattern disappears. But the thing is, if you have a real problem with the variability of residuals, you will see a clear pattern, a clear V pattern here. Well, I would say it's a border case, and the cuckoo plot looks more or less fine, right? There is, by the way, another way to take a look at the residuals. So the blue line here is a fitted curve. So basically what we have just seen in previous graphs. Yeah, like here. And the pink lines where basically it's a fit to the residuals, and you can see that the residuals are distributed more or less randomly along the line. You don't see any patterns in the pink line. So I would say that the residuals are fine. And the problem here might be caused by the fact that the response variable, mean germination time, is not normally distributed. Right, and I'm going to check it by plotting a very simple histogram. So you can see that the values are slightly skewed to the left, right? And let's say any textbook would tell you, if this pattern would be expressed stronger, to take another model, to basically to use a Poisson or generalized GLM with Poisson family or anything else. But like I said, it's a border case, and before you select a more complex, a more complicated model, you might also try modifying your data. And we know that this problem with the skewness can be cured or solved by applying logarithm transformation to a data. Oops. So, give me a second. So when you transform your data, well, you see that the distribution improves. And when you fit now the model with this transformation, so basically we get the very same output. Well, of course, the estimates are different now because we transformed the data. But when you take a look at the residuals, you see that, this slight V-shaped pattern disappeared. And down here, it looks even better, right? So it means that before you start playing around with models, with different fitting holes in our sorting box, you might also apply some data modification here, which is actually legit, right? So, yeah, it looks even better now. So I would simply, go on and report. This is your model output. You could plot the data using the ggplot graph, like here, right? And you could provide the model output to the paper, showing, the significant differences in intercepts or slopes. Right. Ella, do I still need to answer a question?
Oh, sorry, I just sent it before I finished writing it.
So the point here, so what you're suggesting is a so-called p hacking, right? So you don't see any significant, no, sorry, no offense. It's
No, it's fine. It was just a genuine question. Yeah.
And this is how a lot of researchers would proceed. You know, you see some non-significant results in your table, in your model output, and you simply remove it. But the question is, my point here I'm trying to make is that the way you specify the model is the way you ask your questions. Because up here, I'm just interested in a general pattern, right? I'm interested whether elevation has any effects on mean germination time. By including this interaction term, I ask a more specific question, whether this relationship holds for every test temperature. And even if I have some non-significant results, these are my results. And therefore, you know, I'm not really allowed to, you know, now to manipulate the results to get better p-values. Well, short answer would be, you know, it depends on your question. If you're just exploring your data, if you see, well, there are no big differences in the slopes, it's basically the same, but the intercepts are different, you would go back, you know, to this model. But if your question is very specific and you're interested in MGT elevation relationship, different test temperatures, you should stick to this syntax. Okay.
Yeah, that makes sense.
Right. Vanessa, it's a very good question. The question is, again, it depends. It depends on the question you ask. If you're interested in the effects only, because in this particular case, as an ecologist, I'm not really interested in the pure numbers. I don't really care whether, you know, the mean germination time is 18 or 10 or 5. I'm really interested in the pattern. For example, in this particular case, I want to find out whether elevation has an effect on mean germination time. Well, the answer is yes, the results are significant, and I will not even discuss the numbers, transformed or not transformed in the paper, because it's not relevant, right? But for example, if you test seed viability in your gene bank, right, the practitioners, or you personally, would be interested in raw numbers. You would be interested, for example, how long your seeds remain viable in a gene bank. And then you need not a transformed value, right, but a pure true value, 15 days, 100 days, 1 year, and so on and so forth. Therefore, you feed the model with the transformed data, but then to make a reasonable explanation, to write a reasonable explanation of the output, you would need to back transform them. Again, it depends on the question. If you're interested in patterns, I would transform them and just stick to them. If you're interested in the numbers itself, you would need to back transform them. Does it answer a question? All right, welcome. Right. Yes, there are no further questions on that. Again, we're cleaning the environment. And now we will be working with a multiple regression. So basically, we're staying in the same study system. Again, I have different plant species. I collected seeds of those species at different elevations. And in addition to mean germination time, what we have just did, I also have data on seed mass, right, or seed size, seed weight, what do I prefer to call it, and also have data on dormancy. So it's a binary variable. So basically, 0 means that seeds were non-dormant, right? So basically, you put them in a plate and they germinate, and 1 means that seeds were dormant. So meaning that you have to apply a kind of pre-treatment to break the dormancy and to force the seeds to germinate. And this is the data set we are going to work with. You can see no problems here, all numeric variables. And my question is here, whether those 3 traits, well, 3 parameters, elevation, seed mass, or dormancy rank, has any effects on mean germination time. Well, it's a kind of mixture of ecological and biological questions. For example, I know that alpine species might be adapted to the harsh environments, by adjusting their germination speed. So what we just learned from a previous example, that alpine species tend to germinate, well, their germination speed is comparatively slow. I also know that small seeds or bigger seeds might germinate faster because, you know, they have more resources for that. And there might be also some effects of dormancy, right? If you have non-dormant seeds, you put them on a plate, you add some water, they germinate. Whereas some dormant seeds, they might, you know, take a bit longer. First of all, we need to break the dormancy, or we need to after ripen, and then we might germinate after that. So these are my 3 questions asked. And what I'm doing here, I'm running multiple regression. But before I do so, I make a few manipulations. Because here, well, I don't really want to have, you know, the species names in the column. So I use the species names as column names, row names. And in a while, you will see why is it important. So now my modified data set looks like that, right? So this is the data for Tyrannosaurus cristatus, Helictotrichum pubescens, and so on and so forth. Right, there is another fancy way to fish for relationships in your data. Again, it's a kind of mixture of correlation plot and things and pairs. So basically, you can take a look at the, you know, properties of the variables you have in your data set. You can see the data distribution. You can see, for example, there's a seed mass is skewed. So in our data set, we have actually quite a lot of small seeds and a few exceptions. Well, dormancy rank. Dormancy is a binary variable here, so it's either 0 or 1. And you can also see the correlations among these variables. You know, just another way to take a look at your data. Right, now let's specify the model. I forgot to note here to add here another variable, dormancy. So, 2 important things. First of all, this is a multiple regression. So basically, I have 3 working hypotheses, and I ask whether elevation has an effect on mean germination time, whether seed mass has an effect on this parameter in dormancy. Before I run the model, I scale the variables, right? So basically, does anyone know why we need to scale variables here? Why is it important here? Any ideas? Anyone?
Well, I guess you're interested in the relative effects.
Correct.
Variables, and if things have if some of the variables are more variable than others, then that will be reflected in the coefficient, in the parameter estimate. So you scale in order to make them equally variable.
Right. Thank you, Tere. As I mentioned before, I'm an ecologist and I used to think in ecological gradients. And if you want to compare, for example, effects of temperature and precipitation on any parameters you want, seed germination, seed longevity, whatever. Let's say the computer is clever, but at the same time it's stupid. It doesn't really understand your study system. When you compare, for example, variability along precipitation gradient and along gradient of temperature, you will have the same numbers, right? You will have, for example, a gradient of precipitation from 1000 millimeters per year, 1001, 1002, 1003, and so on. The step is always 1. The very same thing you have when you think about temperature. You have mean annual temperature of 80 degrees, 9 degrees, 10 degrees, and so on. Again, the size of one single step is 1. But what is the ecological difference between 1 millimeter of precipitation and 1 degree, well, mean annual precipitation of 1 millimeter and 1 degree of mean annual temperature? Same number, right? But with really strong effects on your biological systems, because 1 millimeter of precipitation is nothing. It's probably 5 drops more. But 1 degree of mean annual temperature in our system would mean 150 meters of elevation, which might be important for some plant species. And by applying this scale function, I make those effects comparable, right? So biologically and ecologically interpretable. So let me see, we have some, okay, it's called dormering. Again, before I take a look at the model output, I check whether I met the assumptions. So again, I don't see any problems here. Well, there is again, the slight V-shaped pattern, but I don't see it in the scaled plot. There are some deviations here in the cuckoo plot, but like I said, it's not a beauty contest, so the model looks fine. And you can see that now, so because I use raw names here, I use species as raw names here. For example, if you have some outliers here or some problematic residuals, you can always take a look, what species is causing this problem, right? It might be useful in your data set. Right, I would say the residual plots look just fine. So we can explore now the model output. Looks again fine. So now I'm using summary. So I can see that elevation has a significant positive effect on the mean germination time. So basically meaning that, the higher elevation, the higher MGT numbers are. So basically alpine species, meaning that alpine species have comparatively low germination speed, right? I can see that there are also some effects of seed mass as anticipated. Well, apparently larger seeds, they take longer to germinate. Well, somehow different to the things we expected. Well, and there is a so-called marginal p-value, but I would be really conservative here, saying that the dormancy is not really related to the mean germination time. There is one quick and handy way to, because those estimates and are kind of hard to interpret. What you could do now, you could use a effects package by plotting those relationships from the summary output in a separate figure. And this is actually, what we observe in our data. So like I said, fast germination in lowlands and fast germination in smaller seeds. So apparently smaller seeds germinate faster as compared to the big ones. Here you have also so-called rugs. So those short lines here, tick marks, indicate the data availability, and you can see that the we have covered basically all elevational bands, ranges here in our data set. Well, here it might be problematic. We mainly have small seeds in our data set with a few exceptions. And you can see that the majority, well, most of our test species have dormant seeds. Right. Of course, you all are interested in, in reporting this data in a report, in a paper, whatever. And, this output doesn't really look attractive. There are a few wonderful solutions how to deal with such kind of cases. This ASSC plot. So one thing would be, you could plot an output from the regression using this function, tap model. And this is what, well, basically, it's the very same model output, right? But in a more attractive way. So you have estimates, confidence intervals, and p-values. You can simply copy it and paste it in an Excel, whatever. please explore this function further. You can actually adjust basically all the elements in the table. You could, for example, report standard errors instead of confidence intervals if you like. You can also make a very nice effect plot based on the model. Yes.
Sergey, could you show how you substitute in that table the confidence intervals with standard errors? Because I tried to do it in the past and I was having issues.
Oh. Do you need the answer now? Because I have a solution somewhere, but I need to look it up.
No worries.
But I mean, for those who are new to R, there's always this option to ask for help. So basically, question mark, the function you're asking can then was it this one? And usually also have an explanation, right? What different parameters do, and usually at the end, we have a few working examples. Well, not here, but usually you can find it there. Here you go.
Okay, cool.
But then you have to, switch off the confidence intervals because it doesn't really make sense to report both of them in this respect, in this context. All right, I think there were a few more comments up there. Yeah. Right. One last thing, you can also make a very nice effect plot based on your model output. Well, Omen is Omen. This is a function plot model. You can also play around with all those parameters here. But what you get here, well, this is basically the graphic output of our model. You can see that, well, the estimates are positive. You can see that we have, well, at least elevation and sigmas are significant. And you can see that elevation and sigmas have a comparable effect on mean germination time because, those estimates are basically identical. Right. Are there any questions on the things we have just? Yes, no, maybe? Oh, you are welcome. Yeah, I have to say, in 2008, when I started my PhD, the things in R were kind of ugly and awkward. You had to code everything on your own, and your scripts were pages and pages long. But nowadays, just you look for a solution, you find an application-ready package for almost everything you need, right? Especially for those classical things like regression. Yeah, just use Google, just ask questions, and you'll find a lot of wonderful solutions. Yes, the SG plot is based on ggplot, right? So basically you could use the very same syntax, the very same commands, right, to adjust its parameters. Yeah, Justin, yes, plot model could be used for interactions. Well, it's an endless package. You can basically apply it to every model you run, to every case. And I think there is a wonderful tutorial in the internet on the SG plot. Just look for it. Just look it up. Guys, I'm sorry, I have to make a short break, 5 minutes. My family called, so I just need to check on them. I'll be back in 5 minutes, okay? You can play with the code while I'm away.
It's probably a good chance for everyone to have a quick 5-minute break. So it's 3:45 now. If we come back at 3:50, and we'll pick back up from there.
Thank you, Amy. So just to wrap it up, what we have learned so far is that the linear regression is a very flexible statistical framework. So what you can do with that is not only, to fit simple linear function to a data, but you could also compare groups of objects like temperatures in our case. Well, in this vein, it's very similar to ANOVA, to the classical test all of you most likely know. They also can run so-called multiple regression. We could test several, usually independent from each other, explanatory variables, their effect on the response, like mean germination time in our case. You could also account for so-called random effects. For example, if you run an experiment in which your objects, plants, petri dishes are in kind of blocks, right? You could also account for those possible effects. So actually this framework can be adjusted to any kind of residual distributions. If you remember, one of the important assumptions in the linear model was that the residual should be distributed normally, which is usually not the case, at least when we deal with seed data. In this case, we need to use so-called generalized linear models. And of course, we can fit a model, we can run a linear regression with any kind of data, numeric, categorical, and even binary data, right? And generalized linear models, we're going to talk about, deal with such kind of variety very nicely. I see a comment in the chat. No worries, Damian. Right. I have here a few links on generalized linear models. Like I said, the internet is full of different tutorials, books, whatever, but I personally find those links very helpful. So they explain in a very complicated and complex matters in a very similar, understandable language. So it's a very good start. I have here also a few slides about generalized linear models. You need to know, of course, if you're interested, if you're into math, you can look it up and read more about it. But what I want you to know about this framework is that basically the GLM, or generalized linear models, is a flexible generalization of an ordinary linear regression. So basically, the computer uses the very same algorithm to fit the line, but at the same time, this algorithm allows for any kind of error distribution, right? So if you remember the model, so in the examples above, in the simple linear models, the residual should be distributed normally, but this generalized linear extension allows for any kind of residual error distribution. Right. This might be a bit confusing for some of you. The word linear in the GLM definition does not necessarily require the linearity of the model. So in fact, the simple linear regression we discussed in the first part of my blog, of my workshop blog, is just one single case of generalized linear models. Right, this is what you just said. So in the examples before, we always assume that the residual should be normally distributed. Again, this is not the data that should be normally distributed, but the residuals, and you always have to check it up. But we know that what GLM does from computational point of view, well, first of all, you specify those models in the R environment in a very similar way as a LM framework. Instead, well, just type GLM, specify a model, and then you have to specify the family. And technically, GLM is just a simple linear model working with transformed data. So by specifying this family, and here you can see a few examples, you basically tell software, you tell R, what kind of error structure your data has, right? So that it fits, selects the right algorithm, the right model to fit to the data. Here you can see a kind of very short guide to the links, right? So if you have, well, if you know that you need to apply a GLM, you need to fit a GLM to the data, this is a very simple guide to decide. Usually, the type of data you're dealing with forces you to select one of those families. For example, this morning we have been, well, before we were working with temperature, which is a continuous variable, right? It could be positive and negative. And usually such kind of temperature data, they follow the normal or Gaussian distribution, right? If you plot the data, you always get, this nice curve. For example, when we talk about distances, right, it's again a continuous variable, but it is always negative. You cannot say that the distance can be negative. Minus 200 kilometers doesn't exist. Usually, such kind of data will follow gamma distribution or inverse Gaussian. When you work with counts, right, and this is mainly the case when we deal with, for example, seed germination, seed variability data. So usually such kind of data will follow so-called Poisson distribution. So they're always left skewed. So you have a lot of zeros, so a lot of values with 1 or 2, and then a few other classes which are less frequent. It might be, we might also work with binary data. For example, dispersal events, where the seeds were dispersed or not, where the seeds germinate or not. Germination percentage, it's a probability, right? It always ranges from 0 to 1. And also proportions. And for the last 3 data types, you always or most likely need to use GLM with a binomial link. I think I'm going to stop here and move to R. So you don't need to change the scripts, everything is in there. And we are going now back to the previous example. And we're going to take a look at the dormancy patterns along elevation gradient. If you remember, I have 78 species collected at different elevations. I have seed mass data for all of them, mean germination time, and I also know, their dormancy status, whether they germinate easily or not. And what I want to do now, I'm really interested about dormancy patterns along the elevation gradients. Right, of course, I could plot the data now, but we are jumping straight to the model. I feed the model, right? So basically, I assume that dormancy rank, dormancy status is influenced by elevation. So I know that in cold ecosystems, like in my alpine environments, plants tend to have dormant seeds. It's a kind of, again, a risk avoidance mechanism, because we have a long cold winter and seeds are usually dispersed in autumn. So if you start germinating right after dispersal, most likely they will be killed as the very first frost. So therefore, most of them have physiological dormancy, well, meaning that the seeds should be cold stratified before, and this cold stratification period coincides with the duration of winter. So basically, it's a kind of lock which prevents, postpones seed germination to more favorable warmer periods. And I expect that, the higher you go, that in the alpine species, the proportion of dormant seeds should be higher. I specify the model, and apparently the answer is no. So elevation does not have any significant effects on the dormancy status in my seeds. However, what we learned, and I hope that